Okay, just as an administrative note, I looked at the course calendar, and we're moving right along. We're not behind in any way. So up to now, it looks like we're still on track to have exam number 4 next Friday, which is the last day before Thanksgiving holiday. If something comes up, please let me know, and we can make the adjustment. We have plenty of days that we can choose from to adjust. I would prefer not to have an exam during the last week because I know there's a lot going on in the last week. But if we need to slip back, there's no problem. All right? So we're continuing our discussion of the root locus technique. This semester, we learned basically 2 classical techniques for designing control systems. One is using frequency response, and we've done that. And we've been looking at the last week or so at this concept of the root locus. So we're going to use the root locus as an alternative approach to designing the control system. Let me make a note also. Let's say that Friday we're going to be back in the lab. Okay, let's meet back in the lab in Shelby 1113. Okay, and so we'll take a look at some tools that will make it life a little bit easier for you when you're, say, working in practice. What we learn in this class is basically how to do things by hand. It's that kind of a sanity check. And learning things to do by hand gives us a little bit of insight of how we might use computer tools because we have a rough idea of what direction we should go in. All right. So let's take a look at a control system, and we'll learn by way of example today. Let's design this control system. Okay, there we go. There's our block diagram of our control system. This is the plant or the process, and this is the compensator. Okay. And so what we're going to try to do today is let's try to design a phase lead compensator. Okay. And so with a phase lead compensator, we have here the 0 is going to be smaller than the pole. Now you may recall we designed this before in frequency response. In frequency response, I used a slightly different form of this transfer function. We used the Bode form before when we were doing frequency response design. In the frequency response design, I wrote it as, I normalized these terms. I called it omega z and then s over omega p, like this. A 0 and a pole. There was a 0 at omega z and a pole at omega p. This was in frequency response. So, but here, I did not normalize it. The reason I don't normalize it is because it makes our math a little bit easier to do things like evaluating the angle criterion and the magnitude criterion, which are the 2 equations we need to evaluate when we design using the root locus. These 2 are just algebraically related, algebraically equivalent to each other, but this is just the form that we are going to use. Let's first sketch what the root locus might look like. Okay. And so if we do a root locus sketch, this is what it might look like. Label our axes real and imaginary. We have the plant is so, a pole at the origin and a pole at -1. Now we're going to add a phase lead compensator. Phase lead compensator means that the 0 is less than the pole. Okay, the 0 is less than the pole, and that means it's going to be closer to the origin than the pole is. So one possible design is maybe put the 0 here at minus z, and the pole here at minus p. Okay. And let's sketch the root locus just using a few rules. An easy thing to do is to first see where on the real axis there may be loci. And so you see the real axis is split up into sections. We stand in any section and we look to the right, and we see an odd number of singularities. And if there are an odd number of singularities, then we should color it in. And so we do that. We color it in like so. Loci start at the x marks, and they go to the zeros. So we have, or they go off the page. So we have a total of 3 loci because there are 3 poles. So one starts here, another one starts at the origin, other one starts at minus p. One of them goes toward the 0, the other 2 must go off the page. We have 2 poles, 1, 0, so the relative degree is equal to 2, so the asymptotes are vertical. I don't know where the asymptotes are because I don't know all my numbers, but maybe it does something like this. We don't know. This is just a rough idea, so this might be a possible root locus. Okay. But the idea is, it looks like using a lead compensator would result in a stable control system. Okay, so it looks like what I can do is I can have closed loop holes anywhere along these locus or these loci, these lines here. Okay, so remember that the root locus is related, where the poles are is kind of related to the transient response. And so let's look at a design specification for our control system and then convert that back into numbers here. So here's an example. Design specification. Okay, so these are the specifications in time. So we may say, for example, I want a settling time. Less than, let's say less than 4, or let's say 3. I keep on using even numbers. Today, let's use an odd number. Settling time less than 3 time units. And let's say an overshoot less than 5% for a step response. Okay. This is a step response overshoot. Okay. So notice these are time domain specs. Okay. This is different than the frequency response. Frequency response, which says things like phase margins, gain margin, stability margins. All right, so we got to convert this basically to some desired closed loop holes. Find the desired dominant poles. This system has 3 poles. This control system has 3 poles, 1, 2, 3. But we're going to roughly approximate things by a second order because these are second order response characteristics. Our system is not second order, it's third order. So we can expect that our actual response won't be textbook because the textbook is for second order. So we're going to find desired closed loop poles, dominant, second order. Okay, these are second order specs, but we know fully that this is a higher order system. But that's what we do in engineering. We use the tools with what we have and try to do difficult problems. All right, so what we'll do is I'm going to say that the poles, they need to lie somewhere over here to the left of the time constant here has to be a fourth of 3, so it should be to the left of minus 4 over 3, wherever that is. Okay. If I choose the real part as minus 4 over 3, that means the time constant would be equal to the inverse is 3 over 4, and that would say that the settling time would be 4 times that. That would be equal to 3. So that meets the specification. See how I went from time units, settling time, back to time constant back to where the real part of the poles are. So they need to be over here, somewhere, bounded by this line at minus 4 over 3. If I come over this way, if I put the real part of the poles over here, the response will be too slow. If I put it over here, then the response will be fast enough. The other thing that is I have to take a look at the overshoot specification, the damping factor. And so we need to find some sort of angle here. This is theta. And remember that the damping ratio is equal to cosine theta. And we know that the overshoot is related to the damping factor. Okay? This affects overshoot. So I could take the overshoot formula, set it to 5%, and then back calculate and figure out what this is, what the damping factor ought to be, or the damping ratio. And then once I know the damping ratio is, I can take the inverse cosine and figure out what the angle theta is. Okay. Now, it turns out coincidentally that a very common idea is that a nice angle that's easy to work with is 45 degrees. Okay, 45 degrees works. 45 degrees has a lot of practical appeal. In my day, if you went to the bookstore and you say, hey, I need to buy a triangle for a drafting class, which is what all engineers took, you had two choices. You had a 30-60-90 triangle, or you had a 45-45-90 triangle. 45-degree triangles are nice because two of the legs are the same length. 45 degrees kind of splits this world up evenly. This part, the real part and the imaginary part will be the same. And so that's very convenient, and so coincidentally, it also will give you overshoot less than 5%. It's actually 4.32% for a second-order system. So what that means is we need to keep not only the poles, the real part, to the left of this line, so it needs to be over here, but we also need to pick poles that are below this line. So if we take the intersection of both sets, then we get an area that's like this. We need to keep our poles to the left of where my pen is right now, and I need to keep my poles inside this sector right here, and the intersection of those is this shape right here. Okay. So we need to pick a point out here. So this is minus 4/3. Let's go ahead and let's just pick this point right there. Okay. So we'll try to do a design. We'll try a desired closed loop pole, find the desired closed loop poles, the dominant poles. We're going to call them S star. We're going to try S star is equal to negative 4/3 plus and minus J 4/3. So there's going to be a point there, and there's going to be a point here. Okay. So in other words, let's go back to our root locus sketch. This is a real, imaginary. What we're saying is we would like this point, S star, equal to minus 4/3 plus or minus J 4/3. We would like it to be on the root locus. And we have to design now this number and this number. Okay, this is known. These two are known. That's the plant, but these two are unknown. Okay. we want S star to be on the root locus. That's the point of root locus design. All right. All right, so for root locus design, we have two equations, as I mentioned before. We have two design equations. One of them is called the angle criterion, which we're going to apply today. And the second one is the magnitude criterion. Okay. Angle criterion and magnitude. We have two design equations. So we can solve for how many unknowns uniquely? Two equations, two unknowns, okay? We can find two equations, two unknowns, all right? All right, but our compensator is K S plus Z over S plus P. And our unknowns are 3. Okay, so what are we going to do? Any suggestion on a way forward, a path forward? You're going to have to choose one, okay? That's one approach, is to choose one. Now, if we remember the magnitude criterion says K equals blah, 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 something. So we have a formula for K. Magnitude criterion is going to tell us K, so it doesn't make sense to choose K. Because we're going to use this equation. We're going to use both equations. One of the equations tells us what K is, so this is really going to be solved for. So that means we're down to choosing Z or choosing P. And if you review some of the old exams, some years, I gave a Z and said design P. Other semesters, I gave a P and said design Z. Okay? So choose one of the parameters, not K. Because we have magnitude equation, and we have the magnitude criterion. We choose one of the parameters, not K. We choose Z or P and hope for the best. Okay? And when I say hope for the best, I'm not joking. Okay? It is possible to choose a parameter unwisely. Okay. For example, I said I don't know what Z and P are. There's somewhere out here. But we could make a poor choice, and then the root locus may not go through this point. It may not be possible to find a combination of Z and P that moves this way. Okay. Hope for the best. If it doesn't work out, we may have to do a different choice. All right, so would anybody like to, staring at this now, would anybody like to make a choice? And we'll work it out together. We're going to work through it as a class. We're going to work out and see if it works. Somebody want to make a choice of one of these two numbers? Okay, here's minus 4/3, minus 1 1/3, plus J 1 1/3. So kind of get a rough idea here. It's minus 1, here's 0. Anybody want to make a suggestion for what this might be? Somebody said, let's choose this to be -2. Okay? So for today, again, I don't know if this is going to work. We're going to try. We're going to try Z is equal to 2. So in other words, now our compensator is equal to k s plus 2 over s plus p. I have two unknowns, s plus 2. Okay, z is equal to 2. Somebody suggested trying z is equal to 2. Okay, so now the root locus problem. Let's do the angle criterion. Always do it first. Always do the angle criterion first. Always. Okay, do it first. Let's take a look at it. I'm just going to draw the upper part of the picture. The upper part of the picture, because the lower part looks just the same as the upper part. This is the real part, and this is the imaginary part. This is now chosen. We chose it to be negative 2. This is negative z. It's negative 2, okay? And we don't know what p is. It's an unknown out here. We're hoping that the root locus will go through this point right here. Negative 4/3 plus j 4/3. Okay, brush out your calculators, guys. We need, okay, so what we're going to do is we're going to warm up those calculator batteries. We're going to draw these lines here. Okay, now I'm going to do it geometrically. You may figure out a way to do it on your calculator faster than I can. I'm going to call this angle theta 1. I'll call this angle theta 2, call this angle theta 3, and call this angle theta p. Okay, now all of these coordinates of most of these x's and o's are known. I know this is at 0, this is at 1, minus 1, this is at minus 4, plus or minus j4. I know this, so I know all these angles. I mean, I can figure them out with my calculator, but this is unknown, okay? So the angle criterion says, let me first write out the equation. The angle criterion says the angle of CG evaluated at S star has to be equal to plus or minus 180 degrees. Okay, the angle of the compensator and the plant. The angle of the open loop has to be equal to 180 degrees. All right? So let me write out equations so you know what we're solving for. So what we're saying is the angle of S star plus 2 over S star plus P, 1 over S star plus 1, this has to be equal to 180 degrees. This is the compensator. This is the plant. This is the compensator. You see it's right here. Notice I didn't write K. Why did I not write K? Because K is going to be a positive number. Its angle is 0 degrees, so let's make my life easier. Just dropped it, okay? But these things are illustrated by these things, okay? So what I can do is I can say, well, I got zeros and I got poles. I got zeros and I got poles. All these factors are knowns, okay? S star is equal to negative 4 over 3 plus j 4 over 3. I should be able to enter that into my calculator, plug in all these things, and so all these angles are known except for this factor. So what I'm going to say is that take the angles of the poles. I'm going to call it theta p plus theta 2 plus theta 3 minus theta 1 is equal to 180 degrees. Let me bend the page down and bring the picture back in. Okay. The angle of the open loop has to be equal to plus or minus 180. And plus or minus 180. Okay? So the picture is that these angles have to add and subtract appropriately to be 180 degrees. So study this, and understand how it is related to this equation and how it's related to this picture. These are the angles to the poles. This is a pole, theta p. Theta 2 is an angle to a pole. Theta 3 is an angle to a pole. So I'm gathering all the angles of the poles together, add them all up. This is an angle to a 0. So I take the difference from the angles of the poles. All that has to be equal to plus or minus 180. And as I mentioned in a previous meeting, this is one of the few places in engineering where you can get terms backwards and get a minus sign wrong out, mixed up, or reversed, and it doesn't matter. I could wrote the exact same equation and said theta 1, put it over here, minus all that, and it would be okay because of this. This is a plus or minus. And because I'm human, I'm kind of like to write my unknowns out in front. I decided to write the angles of the poles first. If we had been trying to solve for a 0, I might have said theta z, and put it out in front. It's really, this is where your personal preferences come in. Now, what I'm saying is here, when I look at this picture, this should be known, this should be known, and this should be known. And there's only one unknown. And so this is the application of the angle criteria. We're just solving for now one unknown. Okay. Theta p is equal to plus or minus 180 degrees plus theta 1 minus theta 2 minus theta 3. Okay, where are common errors that we make? Common errors that we make are algebra errors. We somehow, when we move this over to the other side, we get this messed up. Sometimes we move these things over as a group, and then when we undo the parentheses, we mess up a sign. There can be trig errors. Okay? There can be trig errors. All right, so we're gonna find some of these angles right now. I want to talk through these right now. Now let's find, for example, theta 1. Theta 1 is this right here. Is this ray. It comes from evaluating this point, S star, at the 0. Theta 1 comes from evaluating S star at the 0. It comes from evaluating S star at the 0. So stick this into here. So theta 1 should be the angle of 2 plus negative 1/3. Oh man, this is 6/3, 2/3 plus j 4/3. Pop that in your calculator and see what you get. Somebody tell me. I think it should be the same thing as 2 plus j4. Anybody got a number for me? 63? Is it exactly 60? Well, okay. 63 point something, right? 63 and some change degrees, okay? Now, a good engineer would say, does that look like it could be 63 degrees? Okay. All right. Do the same thing here with theta 2. Theta 2 is going to be this angle. It's this ray, starting from the origin. Negative 4 plus j4. What does your calculator say for negative 4 plus j4? Negative 4 plus j4 is an angle of, did somebody say 45 degrees? 135. Does anybody's calculator say 45? Okay. And I don't, you may have a calculator that will tell you 45 because you enter, and depending on how you enter things in, you may enter in, for example, you may say, I want to take the inverse tangent of imaginary part over the real part. I take the inverse tangent of 4 over negative 4. Okay? What is 4 over negative 4? Negative 1. All right, so find the arctangent of negative 1. What do you get? What do you get for arctan? Negative 45. Okay, so if you do your geometry that way, it's going to, which is valid, right? It's the angle of imaginary part over real part. Your calculator might say negative 45 degrees. You have to rethink this. You say negative 45 degrees. Why did it do that? It's because calculators are set up to try to give you answers between plus and minus 90 degrees. Okay, plus and minus 90 degrees, because we know that trig functions are cyclical. They're periodic. And so you might get this answer as negative 45 degrees depending on how you approach this analytic geometry problem. You say, oh, it's 4/3 divided by negative 4/3. That's negative 1 arctangent. It gives you the answer negative 45. But negative 45 is this angle. We want this angle. So you have to do some mental gymnastics and realize this is not quite correct. It's actually supposed to be 135 degrees. But these two are related by 180. Okay? So just because you're using a calculator, don't trust the numbers that come up on the screen. You have to ask yourself, does the answer make sense? Okay? Now, if you are using your calculator, say, and punching in a complex number, real part and imaginary part, and then doing a rectangular to polar conversion, then probably it will not give you a funny answer. It'll probably say it's 135.
Since they're related by 180, why does it matter?
Okay, so the question is, does it matter since they're related by 180? You could argue that it doesn't matter, but it will matter because, remember, our solution says that everything has to add up to be plus or minus 180. So if we're off by 180, that's okay as long as we have another 180 that's in the picture, because 180 plus 180 is what? And 360 is the same thing as 0, which means we didn't change anything. But if we don't have another 180 somewhere in the picture in the problem to cancel that out, then the multiples of 180 do matter. Okay, so we need to have an understanding of what's going on. So no, it doesn't really matter, but we need to be aware that we're doing something that's inconsistent with this, and we just need to make sure that we do it inconsistently twice. Okay. All right, so we have one more angle to find. We have to find theta 3. Okay, theta 3 is this angle. So you all plug that in. Somebody bark it out to me. What is theta 3? It's this angle. Look, plug this number in. Okay, or let's evaluate this number. Negative 4 plus J4, and stick it into this number.
104.02 degrees.
Okay. This one's exactly 135 degrees. These two have bits that we have to kind of worry about, okay? If you're doing this in floating point in MATLAB or on your calculator, all these little bits will be okay. Now, you may use your calculator a little bit differently. Okay, you may say, I can plug in this number, I can plug in this number, I can plug in this number. Okay, plug it all in, and then just solve for S star plus P, and it'll tell you what S star plus P ought to be. And then you get an idea of where it should be. If you know this, this, and this, and you plug in a -1, then it'll tell you what S star plus P is, and then you can back it out. But we're doing it geometrically today. Okay, so theta P ought to be equal to, somebody tell me, 180 degrees, plus 63 degrees, minus 135 degrees, minus 104 degrees, and let's see what we get. What'd you get? 4 degrees? Okay, let's see if somebody else gets the same thing. You got the same thing? 4 degrees. Okay. Is it exactly 4, or is it 4 with some change? All right. Did you do round off? Or did your calculator, did you try to? Okay. I'm just kind of amazed that it turned out to be exactly 4, but maybe it is. Because I just kind of chose this number randomly. Anybody else get 4? 4.4? Okay, 4.4 degrees. All right, so what does our picture look like then? What our picture is, back to the picture. Let's come back to the picture. We have solved for this, and this thing should look like 4.4 degrees. Does that look reasonable? It looks like it could be feasible. If I put P far enough out, this angle could be maybe just 4 degrees. All right, so looks feasible on the diagram. Okay, so the diagram would say this. I'm going to wipe out everything that I know. This is negative 4 over 3 plus j 4 over 3. So, can you find this point? Okay. What body of math do I need to appeal to?
7th grade.
Some guy says 7th grade math. I don't think so. When I was in high school, this was senior level math. I took Algebra 1 in 9th grade, Geometry in the 10th grade, Algebra 2 in the junior year, and then my senior year I took Analytic Geometry and Trig. But I grew up in the dirt poor hills of East Tennessee. I remember back in those days they were talking about the new math. The new math was coming out in California, which was a very progressive state, of course, compared to Tennessee. So there was a big debate about whether we should do the new math. And we debated in Tennessee for years and years and years. And we finally decided, oh, maybe we will go to the new math. And they said, oh, California's already discovered it didn't work. So sometimes you wait long enough, maybe fads will go away before you have to worry about it. Okay, those of you who grew up in Alabama, where did you learn to solve this problem? Analytic geometry? Okay, you need a little bit of trig. And trigonometry. Where did you go to school? Huntsville. Okay, remind me not to raise my kids there, because it doesn't sound like those kids had any fun. They were doing analytic geometry and trig in the 7th grade. When did they have time for doing things like playing kickball? And all right. All right, so this is the problem we have to solve. I know this distance. This is 4/3. I know this angle. What button on my calculator might solve this problem? Something related to a tangent, maybe, because I don't know this distance, right? But this over this is the tangent of that. Let's call this x. 4/3 over x is equal to the tangent of theta p. This is known. X is the unknown. Okay. 17.3. This is 17.3? Okay, somebody said it's negative 17.3. Okay, I'm putting a question mark right there until somebody else tells me it's the same thing. You got the same thing over here? You all got negative 17.3? Okay, that's a go. Very good. Okay, so we have done the angle criterion. is done. Okay? So this is just high school math.
Oh, wait, so the X is 17.3.
Is X 17.3 or P is 17.3?
P is 18.6.
Oh, X is 17.3. Okay, perfect. I'm glad somebody mentioned that because that's a P is equal to
18.6 for P.
negative 17.3 minus 4/3. Okay, this is where I can get some signs wrong here, okay? Is it a plus or is it a minus? Okay, this is so hard, okay? Why is it hard? Because if I count the number of years between now and back when I was in the 7th grade, that's how many years? It's a long time, okay? Somebody said it rounds off to 16. Does that make sense if this is 16? No, it should be 18.6, okay? You have to, all the time, don't trust the numbers that fly up on your calculator. You say, wait a minute, did I push the buttons the right way? All right. Okay? These are common errors that we can make. Losing track of all these variables flying around. None of the math is hard, but keeping track of things is difficult. Okay? All right, so now the problem is solved. We know this, we know this, we know this. And now what we want to do is, if we've done things right, we have to design K. K is now 1 over CG of S star. And everything is known now. C is S star plus 2, S star plus 18.6. That's the compensator. The plant is 1 over S star plus 1. And we want to find the magnitude of this. Okay. I'm going to call this L1, call this L2, call this L3, call this L4. This is 1 over L1 divided by L2 times L3 times L4, which is the same thing as L2 times L3 times L4 divided by L1. Now, you all are using some really nice calculators right now. One thing that you could do is go ahead and stick in your number S star. And this will pretty much wrap it up for us. S star is equal to negative 4/3 plus J 4/3. We're going to stick that in here. Let's do this with our calculator instead of calculating all these lengths. Okay? I'm kind of old school. I would actually do more analytics geometry, and I would actually find these lengths. And I would plug them all in. Okay? But your calculator is so powerful right now because it can do complex arithmetic. Go ahead and plug all these numbers in and tell me what you get. What?
30.2.
Okay, your calculator, if you put in complex numbers, it should give you a complex result. Okay, don't do absolute. Give me the complex number, or give it to me in polar coordinates.
0.03, net negative 0.00.
What was the angle?
It's at 180.
Did it say 180?
Yeah.
Okay. Did your calculator do? When you plug in all these numbers, you should get a number, a magnitude, and you should get an angle. The angle better be 180. because the angle is 180 because it's going to cancel the 180 from the angle criterion. And if you don't get 180, then you've done something wrong. Okay, you got to go back and check. All right, so you can plug all this in with your calculator, check the number, make sure it comes out to be some real number with a 180 degrees. The 180 degrees will cancel the angle criterion, and then we'll be good. Okay, so do all this and then do this as a homework exercise. So this is lunch. Do this over lunch. Okay? We are done. We'll do some more examples next week of another phase lead compensator. Maybe next time what we'll do is we'll do one where the pole is picked rather than the zero. But it's just two equations. We have to learn how to exercise them. We'll pick that up on Monday. On Friday, let's go to the lab and start MATLAB, and we will take a look at a design tool which may help you for your design project. How do I pick S star?
Yeah.
We had to go through this process like we did this morning about finding some number that is related to the time response. So the question is, how do you pick S star? Typically, the time response is given, and I have to convert that to some number.
At some point you said you just picked it randomly. And I was,
Well, today I picked a settling time. I picked that number randomly, 3. Once that was
I
known.
was confused about because I thought
Yeah,
there was
this
a way
was-
to calculate S star.
No.
You just-
Well, there is a way to calculate S star. Once you know this and this, I would calculate. But today I just chose 3. I could have chose 1, but I just said let's try 3, and you all can see how 3 goes through the problem.